This unit covers Unit 7.1, which is Gravity in the AP Physics C module. Okay. Here we have a couple of slides on 7.1's essential knowledge and learning objective. In particular, notice the formulas that we have on the right-hand side. This one just continues. Please read these at your own leisure. They are kind of important, but I'm not going to cover them in this lecture. Okay, so here are the formulas. On the right-hand side are two formulas that we'll be using for Unit 7. Okay, the first one is Newton's law of universal gravitation. That's the first one on the right-hand side, which is GMM over r squared. It's important to know what all those letters mean. And on the bottom below that, we have the potential energy formula when we're talking gravitational distances. And that's going to be minus GMM divided by just R. Okay, the minus sign is important, and it's also important to remember that it's divided by R, not R squared. On the left-hand side, we kind of have the IB version of a number of formulas. These formulas are also important, but they're not included on the AP Physics formula sheet. You will need to derive these. Okay, so covering gravity as a centripetal force. Okay, this was Newton's proposal when he thought about shooting a cannonball at greater and greater speeds. Because the surface of the Earth is curved, at some point the cannonball will go all the way around and hit you in the back of the head. Okay, now this doesn't actually happen because of air resistance, but this concept does hold. Okay, if we eliminate friction and air resistance, and this is why the moon orbits the Earth. Okay, so he basically came up with this formula that said force is going to be proportional to the product of the two masses, m times m. Okay, I'm going to be using capital M and lowercase m rather than the more common m1 and m2. I like to think of capital M as more of a stationary mass and little m as the moving mass. Okay, we'll see why as we go through some of the slides here. Okay, Newton also said that the force is going to be inversely proportional to the square of the distance between the two masses. Inversely proportional meaning on the bottom of the fraction, square meaning r squared. So his formula was basically that the force of gravity is equal to some constant times the product of the masses, m times m, over r squared. The value for capital G was actually discovered or calculated later by Lord Cavendish. Okay, it was not actually Isaac Newton that calculated G. He simply said that they were proportional, meaning that there was some constant in front. Okay, this formula was eventually improved upon by Einstein's theory of general relativity, but it's pretty good for the level of physics that we're talking about here. Okay, it probably gets you more than 95% of the way there, maybe even 99%. Okay, so that R is important to remember that that is the distance between the center of mass of the objects. Okay, and the minus sign that we see in this formula simply implies that the force is attractive towards the object, okay, or towards zero if we call that object the center, as opposed to away from the object, repulsive. Okay, so Newton also invented calculus, and one of his theorems was the shell theorem, which basically says I can reduce all of the mass of a sphere down to a single point mass at the center of that object. Okay, this is true largely for a sphere of uniform density, which we will be assuming in almost every single one of our cases. Okay, so we can basically reduce an entire planet or star to a single point, as long as you are beyond the surface of that object. Okay. Just a quick warning, read closely some of the questions. Occasionally they'll talk about an object being located a distance away from the surface of the planet, in which case you will need to add in the radius of the planet. So please be careful when reading those questions. Okay, we'll also be calculating the gravitational field. Okay, the gravitational field is a vector. It basically points towards the center of the planet or the star. Okay, everything with mass creates this gravitational field. The larger the mass, the greater the magnitude. Okay, really this only appears, we only worry about this Again, when we're talking relatively large masses, planetary or at least the size of a moon, 10 to the 20th 10 kilograms or higher generally. Okay, this field effectively extends to infinity, and anything with mass is effectively attracted towards the center of it. Okay, and if that's the direction of it, the magnitude is going to be given by the force per unit mass, assuming I put a 1 kilogram mass at that point. Okay, so it's basically force divided by little m. Okay, little m is we use for like test masses or small masses that move around. Okay, so generally big M, big mass, little m, little mass. Okay, so the strength of the gravitational field is simply going to be F divided by m, which, if we use Newton's law of gravitation, turns nothing into gm over r squared. Okay, we've seen little g before. Okay, little g is what we use for close to the surface of the Earth, and that's where we got the 9.81. And we can calculate that if we use the radius of the Earth as well as the mass of the Earth. Okay, in this example, we're actually calculating the gravitational field strength pretty much at the International Space Station, which is an altitude or distance from the surface of the Earth of 350 kilometers. Okay, making sure I convert my units, I find that little g at the International Space Station is not 0, certainly. It's actually pretty close to 9 at 8.78 or 8.8 meters per second squared. Okay, yes, it is an acceleration. Yes, it's also newtons per kilogram. But what's important to realize at this point is that it is not 0. So when we talk about astronauts being weightless at the space station, it's more that they feel weightless. They feel weightless because they have no normal force pushing back at them. Everything on the space station is effectively in free fall, falling at 8.78 meters per second squared. You experience the same effect on various roller coasters or thrill rides, if you go skydiving, anything along those lines. Okay, you will effectively feel weightless, but if we define weight as mass times little g, you are certainly not weightless. Okay, because we don't ever stop with just one object, we could have 2 or more masses, like the Earth and the Moon, or the Sun and the Earth, or any other combination of masses. They do generally have to be fairly large, otherwise one really dominates the other. Okay, so 2 or more, both masses will generate gravitational fields. Like I said, all masses do that. Okay, and we will calculate the net field strength at any point simply as the vector sum of the individual gravitational fields. So if we think of the vector sum, we have like the ability to add vectors graphically or algebraically. A mass that we place at that point will experience a net force from gravity, effectively from both, but it'll simply be equal to m times g sub net. Okay, so here's a little bit of practice. Okay, I have red balls and blue balls. Okay, the blue ball is in the center, and all the red balls are equally located with respect to the blue ball. Okay, and so think about these 4 cases, and in which case will I have the greatest net gravitational force, and in which case will the 2 cases be actually equal in magnitude. Not necessarily direction, but at least magnitude. So pause this and think about it, and I'll continue on to the next slide. Okay, here's another example, okay, where the Earth has a mass, where again, we're calculating the net gravitational field, but in this case, we're trying to find where the net gravitational field strength will be 0, okay, between the Earth and the Moon. We have a little bit of data on the Moon. I noticed I misspelled the Moon, but that's okay. Okay, the Earth and the Moon are roughly separated by 3.85 times 10 to the 5th kilometers, or 3.85 times 10 to the 8th meters when we use standard units. Okay, so to find where the net gravitational field strength is 0, we're basically looking for a point somewhere between the Earth and the Moon. Okay, because the Earth is pulling to the left in the picture on the bottom, and the Moon is pulling to the right. Equal in magnitude, but opposite in direction, so that when I add them together, I'll get 0. So I'm going to pick an arbitrary point. I'm going to call it x equals d, somewhere between the Earth and the Moon. Because the Moon is smaller, I'm going to bet that it's closer to the Moon, but it really doesn't matter where I place it, the math will work out. Okay, so the math is a little bit tricky. If you've never seen this method of solutions, solving this type of problem, it could be very challenging, especially in the middle and pressure of an AP exam. So it's important, I highly recommend paying attention to this solution. So the solution basically goes like this, okay? Since the magnitudes must be the same but opposite, I'll just set them equal to each other. Okay, so gm of the Earth divided by d squared is equal to g mass of the Moon times the distance to the Moon, which is 3.85 times 10 to the 8th minus d quantity squared. Okay, so this is the trick, okay? I'm going to put all the masses on one side, all the distances on the other. Okay, if you notice, the two numbers on the right hand side are both squared, so I can take a square root of both sides. And that's the challenge that most people don't see. A lot of times when you first encounter this problem, you want to expand out that polynomial and work with it that way. That's an ugly approach, okay? You can do it. It's not the prettiest thing, but it can be done. And you'll end up having to solve a quadratic at the end. This is a lot faster, especially if you're trying to do it as a multiple choice problem. Okay, so remember, we put both masses on one side, both distances on the other side, and take a square root. And so I'm left now with d over 3.85 times 10 to the 8th minus d, equaling 9.72 when I use the masses of the Earth and the Moon. Okay, or okay, and that's an easier equation to solve because I can cross multiply and regroup and then solve on my calculator or however else you want to solve it. Okay, so it turns out that d is about 3.49 times 10 to the 8th meters from Earth, so really close to the Moon, okay, about 90% of the way to the Moon. Okay? Just to wrap up, okay, occasionally we'll talk about the gravity inside a planet. Okay, so if you are inside a planet, now the sphere, Newton's shell theorem doesn't really apply. It does in a different way, but it, I cannot take all of the mass of the planet and reduce it to a single point because some of that mass is now outside of that radius, okay, basically on top of me if I think about that picture. Okay, it turns out, okay, that the mass on top of me is perfectly, the gravitational effect from the mass on top of me is perfectly canceled out by all of the mass at a radius greater, okay, outside, below me, okay. Another way to think about it, okay, if I take this line here, okay, all of this mass is canceled out by all of the mass down here, okay. It must be the mass at a radius greater than my radius, okay? So if I wanted to calculate, effectively I'm taking all of the mass at a radius less than me, okay, and shrinking that down to a point and then calculating it. But it must be a radius less than where my location happens to be. Okay, to calculate that mass, remember, we'll frequently be given density. The volume of a sphere is on the formula sheet. The volume of a sphere, if you don't remember it, is 4/3 pi r cubed. And hopefully you know where it is on the formula sheet, or you're smart enough to know that your calculator probably has that formula somewhere buried in it as well. Okay, so just remember, only the mass at a radius less than me. And how do we calculate that? Okay, so here's a graph of gravitational force starting from the center of the Earth. Notice it's 0. And it's very interesting to note when you do calculate it, it turns actually linear. Okay, so it goes linear from the center of the Earth from 0 all the way up to 9.8. And this would be true for any planet, you know, more or less uniform density. Okay. Going away from the surface of the Earth, it drops off with r squared. It is not a flat line. My acceleration does decrease as I go farther and farther away. Okay, some of these things on top, the MEO stands for medium Earth orbit. GEO stands for geosynchronous Earth orbit. Okay, so a lot of communication satellites are located at GEO. and going further and further away, it gets closer and closer to 0. Okay, it is very important to remember that it is not constant. Okay, it is not 9.8 all the way, nor is it a straight line down, but it is always attractive. Okay, thank you.